Okay, so that last example, we knew it was a power model. So now let's take a look at what an exponential model would look like. Um, they're really similar, even in the form that you'll end up writing. It's really similar. There's kind of a big difference at the same time. So this would be an example of an exponential model. So an exponential model describes the multiplicative growth that each time x increases by 1 unit, the value of y is multiplied by b. And so that would look like, so that would look like y equals a times b to the x. Okay, so money displays exponential growth when interest is compounded each time period. So that's what this example is about. So suppose that you invest $100 in a savings account that pays 6% interest compounded annually. After a year, you will have earned 100 times 0.06, which is $6 in interest. Your new account balance is the initial deposit, which is like a y-intercept, plus interest earned. So plus the $100 times the 0.06 for interest, which would be $106. We can rewrite this as 100 times 1 plus 0.06, or more simply as 100 times 1.06. That is 6% annual interest means that any amount on deposit for the entire year is multiplied by 1.06. If you leave the money invested for a second year, your new balance will be 100 times 1.06 times 1.06, which can be simplified as 100 times 1.06 to the second power, which is $112.36. Notice that you earn $6.36 in interest during the second year. That's another $6 in interest from your initial $100 deposit plus the interest in your $6 on your $6 interest earned for year one. After X years, your account balance Y is given by exponential model. Y equals 100 times 1.06 to the X, which fits the form that we wrote up here for an exponential model. So what you're seeing is that rapid growth. So that you'll always see with exponential. So it starts off kind of slow, but then it takes off really quickly at a certain point. So the table below shows the balance in your savings account at the end of each of the first 6 years. The figure shows the growth in your investment over 100 years. It is characteristic of exponential growth that the increase appears slow for a long period and then seems to explode. So that's this part up here. Okay. So this is just back to reiterate some important things. So when we apply the logarithm transformation to the response variable y in an exponential model, we produce a linear relationship. To achieve linearity from a power model, we apply the logarithm transformation to both variables. So we're not going to do that with the exponential model. With the exponential model, we'll just apply the logarithm to the response variable. So that's where it's very similar but very different at the same time. So as a power model, you would apply it to both variables as opposed to both the explanatory and response variables, as opposed to your exponential model, you're only going to apply it to your response variable. So a power model would have the form y equals ax to the p, where a and p are constants. Take the logarithm of both sides of this equation, use the properties of logarithms, it would come out as follows. So the equation log y equals log a plus p log x shows that taking the logarithm of both variables results in a linear relationship between log x and log y. Look carefully. The power p in the power model becomes the slope of the straight line that links log y to log x. If a power model describes the relationship between two variables, a scatter plot of the logarithms of both variables should produce a linear pattern. Then we can fit a least squares regression line to the transform data, as always, and use the linear model to make predictions. Okay, so quick example I'm going to walk you through here, showing an exponential model. Okay, so Moore's law and computer chips. So Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are the data on the dates and the number of transistors for Intel microprocessors. So the scatter plot shows the growth in the number of transistors on a computer chip from 1971 to 2010. So according to Moore's law, an exponential model should describe the relationship between the variables. Okay, so a scatter plot of the natural logarithm, log base e or ln, of the number of transistors on a computer chip versus years since 1970 is shown. Based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between the number of transistors and years since 1970. So if an exponential model describes the relationship between two variables x and y, then we expect a scatter plot of x ln y to be roughly linear. The scatter plot of ln transistors versus years since 1970 has a fairly linear pattern, especially through the year 2000. So an exponential model seems reasonable here. So Minitab output from a regression analysis on the transform data is shown below. Give the equation of the least squares regression line. Be sure to define any variables you see. So, so you can see from this that the only thing that, so the only thing that you're taking a logarithm of is your y or your response variable. Then the rest of it's just your y-intercept, which is right there, plus your slope times your, and there's your x or your explanatory variable. Use your model from part B to predict. So we're just going to use that. Again, this becomes a little strange because this is not actually the number that you're going to use for your prediction, because this would be a logarithm of that number. So then we'd have to follow. We'd have to follow this definition. So this is a natural log, so we're going to do e to the 25.362, which is approximately 1.28 times 10 to the 11th. transistors. This is what you're predicting, not the 25.3562, because that's just the natural log of that. A residual plot for the linear regression. Discuss what this graph tells you about the appropriate. Okay, so the residual plot shows a distinct pattern, which normally we don't really like that, with the residuals going from positive to positive as we move from left to right. But the residuals are small in size relative to the transformed y values. Also, the scatter plot of the transformed data is much more linear than the original scatter plot. We feel reasonably comfortable using this model to make predictions about the number of transistors on a computer chip. So normally we wouldn't like that. We have a pattern here, but the residuals are small in size relative to the transformed y values, and so also the scatter plot is much more linear than the original scatter plot, and so we will take it. Okay, guys, so this is going to be the end of the third video. I'm going to have to put the next example on a last video, so a fourth video, which will be fast, but it won't fit on this one. So one more to go.